Okay, in this lecture, we're going to start our section 3.2 material on solutions of linear homogeneous equations, in particular the theory of solutions of these linear homogeneous equations, and something called the Wronskian, which we'll introduce a little bit later in this section, which gives us useful information about solutions of a second-order linear equation. So throughout this chapter, what we're going to be interested in is an initial value problem of the following form, something of the form y double prime plus p of t y prime plus q of t y equals g of t. So that is a second order linear differential equation with initial conditions of the form y at some time t naught is known, or it's given as y naught, and the derivative of y at the same time t naught is also given. Let's call that initial value y naught prime. So the question that we're going to pose is whether there is a solution of this initial value problem. That is, can we find a solution? And if a solution does exist, let's say that we have maybe found a solution, is that solution unique? Is it the only one? So the answer to those questions comes from the following theorem. This is Theorem 3.2.1 from your textbook. And we would call this maybe the existence and uniqueness theorem. And it's very similar to the existence and uniqueness theorem we had for first-order linear equations. So here's what it says. Let's review it. If we have the initial value problem that we were just describing, so some second-order linear differential equation with initial conditions given at some time t naught, where these coefficient functions, p, q, and g, are all continuous on some open interval containing our initial value t naught. So here, these functions p of t, q of t, and g of t, once we write the equation in its standard form, are all continuous on some interval which contains our initial value, t naught, that is the value of t where our initial conditions were defined, then we are guaranteed that there exists exactly one solution of this initial value problem. So a solution exists and it's the only one, and this solution exists throughout the interval which contains our initial value of t, that interval of continuity. So this existence and uniqueness theorem, very similar to Theorem 2.4.1 from your textbook on first-order linear equations. So let's consider some examples working with this theorem where we're given some initial value problem and we want to know on what interval are we guaranteed a solution will exist. So in this first one, determine the longest interval in which this initial value problem, given here, is certain to have a unique twice differentiable solution. So if I want to apply this theorem, Theorem 3.2.1, the first thing I need to do is rewrite my equation in standard form, the same form that it's given in our theorem as. So let me start by saying if we rewrite this equation in standard form, well, we want our coefficient of y double prime to be 1. We want a 1 y double prime, which means that I need to divide my equation through by t minus 1. And this gives me y double prime minus 3t divided by t minus 1 times y prime plus 4 over t minus 1 times y is equal to sine of t divided by t minus 1. So we start by rewriting our equation in standard form, and that allows us to identify these coefficient functions that we're interested in. P of t is whatever function appears in front of y prime. Q of t is what we were calling the function in front of y. And this function on the right-hand side is what we are calling g of t. And for a unique solution to exist, we need all three of these functions to be continuous. Looking back at our theorem, continuity on some interval is what we need. So let's think about where these functions will all be continuous. Here we can see that P of t, Q of t, and G of t are all continuous if t is not equal to 1. The only way that I have discontinuity in these three functions is if I'm dividing by 0, if t is equal to 1. So here we have continuity as long as t is not equal to 1. So these functions are continuous on the intervals from -infinity up to 1, or from 1 to infinity. And which interval that I'm interested in for this particular initial value problem depends on my initial value of t. Looking back at the initial conditions, we were given the value of y and y prime at the time t naught equals -2. So I want to choose the interval of continuity which contains this initial value, t naught. And so the interval containing -2 would be the interval from -infinity to +1. So I might say the interval -infinity to 1 contains my initial value of t, which was -2. So by making use of our new theorem, Theorem 3.2.1, I know that a unique solution exists on that interval from -infinity to 1. Okay. So let's look at another example of this same sort of problem. Here we have something similar. We are being asked to again determine the longest interval in which the given initial value problem, shown here, is certain to have a unique twice differentiable solution. So in this example, we see that our differential equation is already written in standard form. So we can go ahead and identify our coefficient functions. Here, P of t, the function in front of y prime, is cosine of t. Q of t, the function in front of y, would be 3 times the natural log of absolute value t. And our g of t function, that is the function on the right-hand side, is 0. So here we have a homogeneous second-order linear equation. So let's think about continuity for these three functions. We need all three of them to be continuous on some open interval. And two of our functions are pretty straightforward. P of t and g of t are continuous everywhere for every single value of t. So let me start by saying that this P of t function and g of t are continuous for all values of t that are real numbers at least. And our function q of t, which is 3 times the natural log of absolute value t, is continuous. Well, let's think about our restrictions on t. We know that the domain of any logarithmic function, in particular the natural log, is the set of positive real numbers. That is, we can't take log of 0 or log of a negative. But since we have absolute values around t, well, negative numbers would be fine, because when we take the absolute value, we get log of a positive number. But log of 0 is still undefined, so t cannot be 0 for that function. So here I could say q of t is continuous for all values of t which are non-zero. So here all three of my functions, p of t, q of t, and g of t, are continuous on the intervals from negative infinity to 0 or from 0 to infinity. So I can either take the negative real numbers or positive real numbers as my interval, and which interval I'm interested in depends on my initial value of t. So for this set of initial conditions, our starting value of t was given as 2, which is of course a positive value. So we want to choose the interval containing that number. I might say the interval from 0 to infinity contains our initial value of t, which was 2. So by this existence and uniqueness theorem, that is theorem 3.2.1, a unique solution exists on this interval from 0 to infinity. So similar to the existence and uniqueness theorem that we saw for first-order linear equations, we have a theorem which guarantees the existence of a unique solution of a second-order linear differential equation with initial conditions, as long as those coefficient functions, p, q, and g, are all continuous on an interval containing that initial value of t.